Morning.
Okay, so let's start with BFS, breadth first search algorithm. We completed DFS algorithm, right? To traverse any given graph, right? It can have more than one connected component, and even then we can use DFS, BFS. Okay, let's see BFS. You know the core idea of BFS from trees, right? What was the core idea? So suppose you start with one node, you visit this node and add all the child nodes of this node to the queue, right? To the queue. Say this is 1, 2, 3, 4, 5. You add all these child nodes 2, 3, 4, 5 to the queue, right? You visit this and then add all the child nodes to the queue and keep doing this until the queue is empty, right? Now we have, see the queue is of size 4, 2, 3, 4, 5. I mean, so when I add a tick mark here, it means we have visited and we have removed it from the queue, okay? Next, we visit 2 here because 2 is at the front of the queue. We pop it and insert all the child nodes of 2 into the queue. Suppose it is 6, 7, 8. You add 6, 7, 8 into the queue. Okay, this is visited. Next, pop from the queue 3, right? And suppose it has child nodes 9 and 10. So this is visited, add 9 and 10 into the queue. So keep doing this. Pop this, add all its child nodes, pop this, 5, and add all its child nodes. Keep doing this, right? So if you look at it, we will get the order of visiting for these nodes as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So this is called level order traversal, breadth first search traversal, or level order traversal. And what did we use here? We used a queue. We used a queue. And we will use a very similar idea for breadth first search for graphs. This was a tree, right? We covered this in the tree data structure. So we will cover BFS for graphs. Okay, next. Now let's look at the top function here. The top function here is exactly same as the top function of DFS, right? If you remember, see, we had the same top function, mark each vertex in B with 0 as a mark of being unvisited, count is equal to 0 for each vertex. If it is unmarked, BFS of B. Okay, in BFS, what do we do? Mark that vertex or node, okay, increment the count, mark that vertex V with the counts, this is V, and mark it as count, and initialize a queue with V, right? Suppose our queue is V. While queue is not empty, for each vertex W in V adjacent to the front vertex. So we have V. So what are all the vertices that are adjacent to V? Say W1, W2, W3, W4, right? And if that child node is marked with 0, that means if it is unvisited, if unvisited, then what do we do? Increment the count, right? Increment the count, mark this child node with the count, and add to the queue. Again, if this is unvisited, increment the count, mark this, and add that node to the queue. If this is unvisited, right, increment the count, mark this node with the count, and add this to the queue. Suppose this is visited, right? Suppose this node is already visited, then we will not expand on this, right? We don't need to cover this. So if we don't need to cover this, what does that mean? We will not add W4 to the queue, right? We will not add it to the queue, and we will also not mark it because it is already marked. It is already visited, right? If it is already visited, we will not revisit it again. So that's the idea. Make sense? So it's
Professor, could I ask a quick question?
yes, sure.
So with the depth first, I get the whole marking the nodes, right? Because we're going down and then back up. And we don't want to visit something twice. But when we're doing level like this and we're going from left to right, I guess I'm having a hard time visualizing when something would already be visited.
Right, we will see an example. Right?
Okay.
So this is just the higher level idea for arbitrary node, right? Then we will apply this concept on a simple example.
Okay.
Okay. And then remove the front vertex of the queue, right? This is there. Make sense? So this is the high level idea, right? So what is new compared with the BFS of tree? Anyone? What is new compared with the BFS of tree?
Well, we need to mark each node. We don't mark them in a tree.
Right? This if condition. This if condition really. We will add this block only if it is unvisited. If it is already visited, we will not add it. So did we have this condition in trees?
No.
No, right? Okay, we will see an example. So here, what they have shown in the example will be the levels, right? The levels will look like this, right? We will think about it later. Okay, let's start with A, right? A, let's start with A. Okay, where shall I write here? Maybe this one, A. A. So you increment the count and visit this, then you add all the child nodes, right? So what are the child nodes? B, E, F. So what we will do is we will add the child nodes and visit them in alphabetical order, right? B, E, F are the child nodes of A, right? We will strictly follow this alphabetical order. We will not visit F first. We will not visit E first. We will visit B first and then E and then F because they're alphabetically sorted, right? Okay. So B, E, F are the child nodes of A. So we will add it to the queue. Anything else is left, right? And all these are unvisited, right? So we will add it to the queue. Next, what else do we do?
We'll go to B.
We will go to B, right? So you can visit this to increment the count, mark B with 2, and then what do you do?
You go to C. And F, but F has been visited. A.
Expand B, right?
Yeah.
Expand B in the sense, add all the unvisited child nodes of B or unvisited neighbors of B into the queue, right?
Yeah.
So initially the queue was like this, and now it became say BEF. You can say BEF, and now you can see it looks like this: EF, B. What are all the child nodes of B?
Just C and F and A.
So let's also add this, right?
Yeah.
See, whenever you add the nodes to the queue, you mark them and then add the nodes to the queue. So they are already marked 2, 3, 4, right? So B, the child nodes are C. C is unvisited, right? C is unvisited. What else? A, what about A?
A is visited.
A is visited. So you cannot add it, right? Okay, what about F?
Also visited.
F is visited, right? So we cannot add A, we cannot add F. So the only option for B is C. Correct? C. So we mark C with 5. And then what do we do?
We go to E.
See, this is the queue contents, right? This is the queue contents. So here I'm just showing you the tree expansion. I mean, the way in which this graph is visited, you can think of this as a tree, right? Okay, so C is visited. Then, so what is at the front of the queue? E, right? What are all the child nodes of E? So let me move to one step here. See, this is the next level, right? Level in, I said this is level order traversal. This is level 0. This is level 1, right? See, you can think of this as a collection of concentric circles. Look at this, a collection of concentric circles. BFS is like concentric circles. So you visit, this is level 0, all nodes at level 0, all nodes at level 1. Level 1 in the sense they have a distance of 1, right? The number of edges is 1, something like that. And then all nodes at level 2, they have a distance of 2 from the starting vertex, distance of 3 from the starting vertex, number of edges 4 from the starting vertex, so on, right? You expand and add or visit the nodes in this concentric circles. See, this is level order traversal. So see, okay, what about E? What are the child nodes of E? A,
F, and I.
F, I. A is visited, F is visited, I. 6, right? What about F? B is visited, A is visited, E is visited, I is visited. So nothing, right? Nothing. So your Q will be something like this. F, C, I, and then F is gone, C, I, right? Let me move to next slide here. See, this is level 2. Is this level 2?
Yes.
C, I are the nodes in level 2. This is level 0. This is level 1. This is level 2. If you look at it, they are like concentric circles, right? This was the center. This was the next concentric circle, right? So this is the third concentric circle at the third level or the second level, so on, right? Make sense?
Yes.
And then what do you expand? C. So what are the child nodes of C? B, D, G. B is visited, so D, G, right? So D, G. So this is 7, 8. Okay, and then expand I. M, N. M, N.
And
9, 10.
and J.
Oh, J, J. You also have J, right? 11. Do you have anything else here? Right? So what do you see? In the next level, you have D, G, M, N, J. That's level 3, correct? Right? So that is level 3, 0, 1, 2, 3. So it's like this, level 3 concentric circle here. Make sense? So you keep expanding like this and cover all nodes. That's your BFS algorithm. Got it? So see, whenever you are given a graph, you can write the queue contents like this. You can write a tree expansion like this, right? How the visited nodes, and you can also see this level order traversal and everything here, right? And give the order of visits like this. See, finally, what we want is this order: A, B, E, F, C, I. Right? See, when we say that you have to visit the nodes in alphabetical order, right? And starting from a particular source vertex. So that is A, that is also alphabetical order, right? We selected the smallest one here. So whenever any student solves this problem, there is only one order you should get, right? It's objective. You can compare whether this order is correct or wrong. Make sense?
Yes.
So you should get this order. See, finally, you need to output something like this. This is the order of vertices. And why are we, struggling to understand all these ordering? Because see, for a simple graph, it is easy, right? You can order it in any way, right? But we want algorithms or programs to scan all these nodes in an automated way. Think about internet, right? So Google, when it crawls billions and billions of web pages, it should use a graph traversal algorithm, right? And can you tell me what is the edge there? What is the meaning of an edge? And what is
It's a URL, right?
Right, a URL, or you can say a web page, right? A particular web page present at a URL is the node. A hyperlink is the edge.
Oh, that's interesting.
Right? Hyperlink is the edge. Similarly, in Wikipedia, suppose you want to download the entire Wikipedia so that you can read it offline. So what do you need to do? You can write your own program, crawling all Wikipedia pages and downloading the entire Wikipedia web encyclopedia, right? How? You need to use a graph traversal algorithm. Something like this, either DFS or BFS. Think about Facebook. Suppose you wanted to crawl the entire Facebook. Yeah, I don't think you can do it, right? It's not like in the public domain, right? Like Wikipedia. But suppose you had the power, right? Then you can write a graph traversal algorithm like this and visit all the nodes. There, nodes are profile pages. And what is an edge? A friend, right? A friend there. Similarly, LinkedIn, so on. See, so whenever you want to traverse a graph, you have to use these fundamental traversal algorithms, right? You shouldn't visit already visited web page or profile. That's why we have this visited concept. And that visited concept, we did not use 0 or 1, true or false. We used a counter. If count is 0, it is unvisited. If count is non-zero, say 3, 4, 17, 1 billion, then it is visited. And the visit number is that count itself. Right? Make sense? Questions?
Professor, I was trying to implement this on Monday. I was having a lot of problems. And I guess my question is the whole visited thing. So before, when we mark something as visited, we're making a separate array or something marking each object that's as visited. And then we have to search that before we add something else again. Is that correct?
Right. See, there are multiple implementations for the same concept, right? One is you can think of uh, a vertex array, vertex itself as an array, right?
Right.
Okay. Then the visited is another array,
Correct.
right? So, for example, visited of I is the ith vertex. So you can number the vertices from 0 to n minus 1. Visited of
I
I
see.
gives you whether the ith vertex is visited or not. Vertex of I,
Okay.
right?
Yeah, I got it to work for integers. You know, if you do integers and the integers go into the individual indices, that's fine. But if you're trying to make it generics, it gets a little more difficult. But that making another array with the vertex numbers is clever. Thank you.
No, this is one idea, all right?
Yeah.
But I think in real life, what they use is 0 to n minus 1. They consider a class for vertex. It is a class.
Oh, then you just make an instance variable of visited or not.
Then exactly, you just have a variable called visited. So then you can do what? Vertex dot visited.
Yep. Oh, that's interesting too. Okay, thank you. Thank you.
This
That's
is
very helpful.
more of object-oriented programming.
Yeah, that's very helpful. Thank
Right?
you.
This is just for coding in a fast way, but this is real object-oriented programming.
Right, right. Thank you. Thank you.
Okay, so that's about BFS, right? Level order traversal. Okay, now let's think about exhaustive search as whole, right? We were looking at exhaustive search, or you can say brute force as one technique, simple technique, very simple technique. So what are the pros and cons of this? Negative is definitely something called combinatorial explosion, right? So what is the meaning of this? See, for many problems, the number of solutions you need to touch in the solution space, it's combinatorial, it's exponential, right? 2 power n, n factorial, n by 2 factorial, whatever. So all these are very big quantities, exponential time. So scanning or touching all these points itself takes a lot of time. That's called combinatorial explosion, right? So any exhaustive search algorithm, right, on a combinatorial problem, automatically the time complexity will be super high, exponential time, right? So these, like, most often are not the efficient algorithms that we are interested in, right? So even for very simple problems, if n is equal to 20, think about 20 factorial, it's huge. N is equal to 30, think about 30 factorial, it's huge. Probably you will not be able to solve that problem with 30 factorial on your computers, right? See, that is combinatorial explosion. And think about dimensions also, right? See, if the number of dimensions change, suppose for 4 or 5 dimensions, it becomes impossible, right? Suppose your complexity is something like 2 power d, where d is the number of dimensions, right? So dimensions need not represent the normal physical dimensions only. It can be the number of columns, the number of features, right? As conceived in machine learning, it can represent many things. Number of features itself is dimensions, right? The number of columns in your say Excel sheet, that's the dimensions, right? The number of fields in a record, that's dimensions. Anyway, so that will be huge. That's a flaw. Positives. Many a times we will not know what is the best polynomial time algorithm, then probably this is the only way to proceed, right? Then we have to use this. And there is a powerful problem solving methodology called backtracking, right? Backtracking. And backtracking is based on exhaustive search. Exhaustive search plus pruning. Pruning in the sense cutting the entire, for example, suppose this is your exhaustive search, you're scanning everything like this, right? Maybe if a condition is not satisfied here at this point, you can prune the entire subtree. Pruning is cutting. So if you cut the entire computation at this subtree, think about how many computations you will be reducing. Maybe here also you can cut, right? Because some property is violated, right? So when you add pruning to this exhaustive search, automatically you get another algorithm design technique, backtracking, that is very famous, right? To solve a lot of combinatorial problems, backtracking. Okay, next. So this even if it is slow, it can be fast for some small instances, right? Than super efficient algorithms. So you might have to use this for small instances. And there are many other advantages. We need not go deeper there. Okay. Right, so that's about the first approach that we covered, exhaustive search. Yeah, let me quickly cover one more problem and then we will move to next design technique. Okay, suppose you want to generate random permutations of a given array, right? So what's the best way? See, if you think in a naive way, right, you can have a loop from I is equal to 1 to n minus 1, swap ith element with a random element of the array, of the entire array. So swap the first element with some random element of the entire array, swap second element with some random element of the entire array, keep doing it until for n minus 1 steps. So this is the normal thinking, right? Naive thinking. But this will not give you random permutations, will not give you uniformly random permutations. Whenever we say random permutations, we mean uniformly random, right? Every permutation should occur with the same probability, right? So this algorithm will not give you uniformly random permutations. That means some permutations will occur more often than the other permutations, right? The probability of occurrence of some permutations are more compared to some other permutations, right? That's not the definition of uniformly random, right? So a good way to implement this is, see, swap of the ith element with a random element from I to n in a sub-array, not the entire array, in a sub-array from I to n. Okay, we will not go into the proofs of this, but just remember, because you might have to use random permutations in a couple of applications. So see, the algorithm design
Professor,
is not straightforward. Yes.
quick question. So here, when you swap, like the second approach, so you include the I itself, right?
Yeah, I mean that's fine. That is fine.
Okay. Just a question. It's not a doubt. It's just a question.
Right. I mean, you could have written I plus 1, but this is also fine.
Okay.
Okay, next. I will not cover bubble sort and selection sort. These are very simple algorithms that you can read yourself, right? I will just give you a high-level idea. So what do you do in bubble sort? You compare two adjacent elements, right? Like this. If they are out of order, you swap, right? Compare two adjacent elements. If they are out of order, you swap. Keep doing it, right? First element with the second element with the third element with the fourth element, right? So on up till the end. If you run this process, right, at the end of this process, you need to get the largest element at the end. largest element at the end. Does this make sense? So, right? Compare first and second element. If they are out of order, swap. Compare second and third element. If they are out of order, swap. Keep doing this till the end. At the end, you should have the largest element as the last element. Okay, so that is one iteration. Now you have the remaining array, right? Repeat this process. When you repeat this process, the second largest element will occupy its correct position and recursively solve the other subproblems like this, right? So after iteration 1, you will get something like this. Largest will be in its correct position. So after second iteration, largest was anyway in its correct position. The second largest element is also in its correct position. So if you have a couple of iterations like this, right, approximately n iterations, you will make sure that you will sort the entire array. This is called bubble sort. Why is it called bubble? The largest element is bubbling, right? Up or down, whatever way you think of, right? So this is called bubble sort. Selection sort. So what is the meaning of selection sort? What is the intuition behind selection sort? So the idea is simple. You scan the entire array and find the minimum element of it, right? And suppose you found the minimum element here. Swap it with the first element, right? Swap it with the first element. Now the smallest element or the minimum element occupies the correct position. You have the remaining array. After one iteration, the smallest element is in its correct position. Now what do? You have the array of size n-1. Again, find the smallest element in that array and swap with the first element of this remaining array, right? So the second smallest element will be placed here. The smallest of n-1 elements here is same as the second smallest of the entire array, right? So after second iteration, the second smallest element will appear here and you recursively solve the other arrays, right? Sort the remaining array. That's the idea, right? So that's the idea of selection sort. Okay, so try to understand the code here, the exact step-by-step procedure, indexing and everything. But that's the high-level idea of bubble sort and selection sort. So there is one more sorting algorithm. We will not cover this, right? You can consider this as out of scope. Counting sort. We will not cover this. Okay, so that's it about brute force technique. Now let's move to decrease and conquer. So what is decrease and conquer? Decrease and conquer is another very powerful algorithm design technique, right? It's a good algorithm design technique. And your binary search, you have learned about binary search, right? Binary search belongs to this category, decrease and conquer. Okay, so there are three types of decrease and conquer. Decrease by constant, decrease by constant factor, variable size decrease. Okay, so we will understand this one by one. Decrease by constant, we will see one example. Decrease by constant factor, we will see two examples here. Binary search is also in this category, decrease by constant factor. You understand this, right? In binary search, what did you do? You divided the array size by 2 the subproblem size gets reduced by a factor of 2 in every iteration, in every step. So that is decreased by constant factor. The subproblem size is decreasing by a constant factor. It might be 2, 3, whatever, right? That's this. That's the most important of all these categories. Then you have variable size decrease, right? We will see one very important problem, selection problem. Okay, so what is the core idea of decrease and contour? You want to solve a problem of size n, So there are 3 steps here: decrease, conquer, combine. So what is the idea here? You decrease the problem size to a smaller size, right? So you get a subproblem of size n dash. N dash is less than n. And then you recursively solve the subproblem. Let's call it a sub-solution. Solution to the subproblem, let's call it a sub-solution. And you combine this sub-solution with some other steps, and you get the solution to the original problem. This is the high-level idea of decrease and contour. Okay, what is this n dash? N dash, okay, do we have more details on this? Yes. N dash can be of this form n minus c. If it is of the form n minus c for some constant c, it is called decrease by constant type, right? If n dash is n by c, that means the subproblem size is decreased by a constant factor of n, right? N by c, then you call it decrease by constant factor. If n dash is equal to n minus c, right, for some variable c, that means every iteration this c is changing. For step 1, it can be n by 2. For step 2, it can be 1. For step 3, it can be root n, whatever, right? It can keep changing at every step. Then it's not decrease by constant, right? Decrease by constant means this c will remain the same throughout the steps till the end when the base case is called. But here this c is a variable c where in every step that value keeps changing. The subproblem size is decreasing, but not at a constant rate, right? So that's the idea, okay? So let's look at some of the examples here. The size of the instance, as we discussed already, is reduced by the same constant in every step of the algorithm. Decrease by 1 is common, right? You can call it linear search or something like that. Decrease by 2, there are some examples also. Anyway, array sum. Think about a linear array sum, right? That all these are linear algorithms. Array sum, array search, finding max, integer product, exponentiation, topological sorting. So here, let's take, say, array sum. So this is, you want to find the sum of all these n elements, right? What you do is you recursively call sum of n minus 1 elements and add it to the last element. That will give you sum of n, right? See here, the problem size decreased by 1. And this 1 is constant. So this will reduce to sum of n minus 2, right? Plus 1, plus this value, right? This is decrease by constant. And similarly, you can apply similar ideas for array search, linear algorithm for integer product, linear algorithm for exponentiation, so on. Okay, simple idea. Next, decrease by constant factor, reduced by the same constant factor. Binary search, right? In binary search, what happens? So initial size is n. So once you decide you are searching in the left half of or the right half, the size decreases by a constant factor, 2. Suppose you decide to go in the right half, doesn't matter. The size is decreased by a constant factor, right? So on. So if you look at it, the number of iterations or steps will be in terms of log n. It might be 2 or 3 or right, something like this, based on whether it is n by 2 or n by 3, right? So on. Search or insert or delete in balanced search tree. Think about balanced search tree. There also, you were decreasing the number of elements to be searched at almost the constant factor, right? Say 2, around 2, approximately 2. Approximately 2 or 3, right? Something like this. Hence, the search time or insert time or delete time in balanced search tree are all log for the exact same reason, right? Then we will see probably 2 problems later, right? Fake coin problem and Josephus problem. We will see that probably in this session. Next, variable size decrease. So here the size of instance is reduced by a variable size at every step. Selection problem, quicksort. So many people say that quicksort is a divide and conquer algorithm, but by the types we have defined here, right? This was defined by Anani Levitin, the author of our algorithms textbook. I mean, he is awesome in defining all these taxonomies, right? So as per our definition, quicksort ideally belongs to a decrease and conquer algorithm where the decrease is, the size of decrease is variable. It's a variable size decrease, right? Quicksort and selection problem are some of the most famous problems in entire computer science. What about searching in a binary search tree? Is this decreased by constant factor? No. Right? See, if you are given a tree like this, then the decrease is by constant. But in a binary search tree, anything can happen. See, it can, at some step, it can decrease by probably half. In some steps, it is decreasing by just 1, right? Anything can happen based on every step, right? Comparison. So in a binary search tree, where you cannot give a guarantee that the height is log, right? So that is a good example of a variable size decrease, right? Okay, next, interpolation search. Okay, you need not worry about this. Now, let's start with decrease by constant. Topological sorting. This is a wonderful problem, right? We will cover just one example, one algorithm here that shows decrease by constant. Topological sort. So what is a topological sort? So we will see some examples also later. First, let's see the problem. Topological sorting of vertices of a directed acyclic graph is an ordering of the vertices v1 to vn in such a way that there is an edge directed towards vertex vj from vertex vi, then vi comes before vj. Seems complicated to understand, right? So what are we saying here? Topological sort of a DAG, this is called a DAG, directed acyclic graph. Why did we say this? Why did we say this? Directed acyclic graph. You know, directed graphs are more generic than undirected graphs. Okay, directed graphs. Acyclic. What happens if there is a cycle? If there is a cycle, then there is no topological order. You cannot topologically sort. Okay, we will see an example later, but and the reason why. It has to be acyclic. There shouldn't exist any cycle in that graph. It should be directed. It should be acyclic graph. Okay, then there exists a topological sorting. Okay, what is that topological sorting? It is an ordering of the vertices. You have n vertices, you need to give the order of vertices, right? Such that if there is an edge directed towards vertex J from vertex I, Vi to Vj, see if there is an edge like this, in that order that you want to output, Vi should come before Vj. Make sense? Vi should come before Vj. So what is the best example of this? See, you can think about courses. So, okay, let's take this example and then I will give you an application, right? Okay, so here is the directed graph and here you have the topological sort. Now look at this. This is the directed graph. The topological sort is A, B, C, D, E or B, A, C, D, E. So there are two different topological sorts here. Okay, what about this graph? There is no topological sorting. Why? Because there is a cycle. So in the topological sort, what's the idea? See, if there is a directed edge, C must come before D, and D must come before E, and E must come before C. Oh, that's impossible, right? So if there is a cycle, it's impossible to have a topological sort. Okay, fine. The meaning is fine. What is the application of this? Very simple. So suppose these are the courses you need to take. Courses you need to take. Suppose I say that course A is the prerequisite for course C. Course B is the prerequisite of course C. Course C is the prerequisite of course D. Course D is the prerequisite of course E. Course C is the prerequisite for course E. Right? Suppose this is the prerequisite graph. Then it is impossible for you to take course D first. Correct? Or you cannot take course C, or you cannot take course E first. Why? You need to follow the prerequisites. So this sorted order is something like the order in which you meet all the prerequisites. Right? Simple example. You can, so if you take courses like this, there is no violation of this prerequisite rule, right? You are taking C before D, C before E, D before E, B before D, B before E. Everything is met here. All the constraints are met here. Similarly, you can consider B, A, C, D, E. All prerequisite constraints are met here, right? So this is one of the best examples, right? It's not only for courses. I mean, there are several applications in real world where there is a dependency. You can only go to say, get document A before getting document C, getting document C before getting document D. Then you need to follow this order itself, right? In how many, all possible ways in which you can follow is given here, right? So that's the idea.
Hi, Professor. I just have a
Yes.
question.
Yes.
How's topological sort different from breadth first search?
Breadth first search?
Yeah, isn't that aren't they similar, or like are they the same? Because if you look at topological sort as a level order search, right? A and B is on one level, C is on another level, D and E is on the third level. And we'll go with that
Okay,
one.
so I mean, we can say that. See, if we don't pose a rule, right, that you need to start from alphabetically first, you can start from E, unless forced, right? That you need to start from A. You can start your scanning of the vertices from E in you BFS or DFS. If I explicitly state that, use the alphabetical ordering, only then you can start from A. If that is not given, you can also start from E. Isn't it? Think about this as a Facebook graph or Wikipedia graph. Is there any rule that is restricting for you to not start from E web page? No, you can start from E also, this web page or this profile, right? You can start from any profile.
Well, this is a directed acyclic graph. What if the direction is is the opposite, like goes the other way? Then you can start with E, right?
No. So even with this, right, you can start with E if the constraint that you have to follow alphabetical ordering is given. You can start from E in BFS or DFS.
But isn't this a directed acyclic graph? So you have to follow the direction. That's why you start from the A.
No. So
No?
only the topological sort has that constraints, right? Such constraints were never given for BFS, DFS, right? We didn't give any such constraints when we defined graph traversal. We just said, traverse the graph. Okay, so the constraint I specifically gave was follow alphabetical ordering. That is because it will help in grading, right? See, if you give a solution from E, every student gives different orders, then it will be too difficult to objectively measure whether you applied that rule or not. Hence, we added our own restriction that, follow alphabetical ordering, right? You start with A. But in real life, in say Wikipedia, there is nothing that is stopping you from scanning this web page first, correct?
Okay.
But you cannot do that in topological sort because you cannot take this course, right? E first. That's not possible. You have to follow this order.
Okay.
Make sense?
Mm-hmm.
Okay. And now think about this. There is no topological sort here, but is there a BFS ordering or DFS ordering? Yes, there is, right? You can always traverse any graph in the world. But if there are cycles, there is no topological order, right? Okay. Next. So there are two good algorithms to solve this problem. One is based on DFS. One uses the concept of DFS, right, to solve. But we will not cover this, right? We will not cover this. We will use a different algorithm. And I want you to learn this algorithm, source removal algorithm. So the idea is beautiful here. So the topological sort is really the order in which those vertices are removed that have 0 in degrees. Okay, so before we proceed, you need to know something about degree of a node. So let's define something called in degree, out degree, and degree of a node or a vertex, right? What is the in degree of a vertex? The number of edges pointing to that node is the in degree of that vertex. What is the out degree of a vertex? The number of edges Going out of that node is the out degree of that vertex. So what is the degree of a vertex? Summation of in degrees and out degrees of a vertex is called the degree of that vertex. Correct? Make sense? In degree is okay. In internet, right? Google search and all, it is called in links or out links. Correct? The number of the number of web pages that point to your web page is the in links, or all the in links. The number of web pages, or the web pages that your web page points to, those are the outlinks, right? In links and outlinks of a vertex or a node, right? Similarly, if Facebook was a directed graph, A can be a friend of B, but B need not be a friend of A. I mean, suppose we had something like this, probably using a follow, right? Probably this would be a better. A follows B, but B need not follow A, right? In Twitter and other social websites. So here, this can be a directed graph, but a friend in Facebook, if A is a friend of B, then B is a friend of A. So it's an undirected graph, right? But if you have something called follow in Twitter and other websites, it's a directed graph. A can follow B, but B need not follow A. B can also follow A, but these are two different relationships, right? Okay, anyway, let's come back. So what is the idea here? Now look at the in degree of all these nodes. Now look at the vertices that have in degree 0. Can you tell me what are the vertices here in this graph that have in degree 0?
A and B.
A and B. So you can delete either A or B, right? Let's delete A. I mean, you could have deleted B also. That's totally fine. Let's delete A. Once you delete A, you get a graph like this. So once you delete A, you are also deleting all edges that are coming out of A, right? Okay. Now you have a graph like this. Now tell me, what are the vertices that have in degree 0 here?
Just B. Just B.
Delete B. Delete B, that means you are deleting all edges that are coming out of B. You get this graph. So what vertices have in degree 0? C. Delete C. You get this graph. So what vertices have in degree 0? D. Delete D. Okay, which vertices have in degree 0? E. Delete E. You get null, right? Nothing. That's your topological sort. Look at the order. A, B, C, D, E. That's your topological sort. Simple, right? You could have deleted B also. You can see if there are multiple vertices that have in degree 0, you can delete any of them arbitrarily. You can break the tie in any way you want, right? If you have multiple vertices with in degree 0. I mean, you could have deleted B first, and then A, and then C, D, E. This is another topological sort. So you can either answer as this order or this order. So if I specifically say give all possible topological sorts for this graph, you need to write both. Make sense?
Yes.
So a very simple algorithm, right? Whenever the in degree is 0, delete that vertex. That So the order in which you are deleting the vertices will be the topological order. Done. I mean, what is the intuition behind it? Think about it. In degree 0 means what? There are no constraints. There are no prerequisites. Satisfy that particular course, right? So here in degree 0 for A and B means that there is no prerequisite for A and B. So you can satisfy that course. I mean, take that course. You're taking A and remove all the edges coming out of A. You have finished off with that course A. Then look at the vertices that have in degree 0, that is B. So satisfy that course. Take that course, right? Remove that course. So on, right? Very simple algorithm. Source removal algorithm. So that's it. So here is the pseudocode. Topological sort, T is empty first, right? Mark each vertex in V as unvisited. Find in degree for each vertex, right? So what if there is no vertex with in degree 0? What does that mean?
Means you have a cycle.
Right. Suppose there are vertices, but there are no vertices with in degree 0, then it means there is a cycle, right? So think about this one. What is the in degree of this? 1. In degree 1. In degree 1. So you have 3 vertices, but you cannot find any vertex with in degree 0. That means you cannot delete it, right? So that means there should be a cycle. So you can use this algorithm to also find cycles in a graph, detect cycles in a graph, right? Cycle detection algorithm, right? So a tiny change to this can also lead to another algorithm for cycle detection in a graph. Okay, next. For each vertex V in V, if in degree is 0, then add it to the queue, mark V as visited. Right? Okay, so at the end of this, what do you get? Why do we need to do this? So how many queues will be there? How many queues would be there here? Is there only one queue?
Are you asking how many are in the queue or how many actual queues we're having?
How many queues will be there in general here? There is only one queue?
No, you're making it looks like because it's in a for loop. So you're making
It's the same queue. It's the same queue, but I can also ask this question here, BFS. Now that is another difference you can see, right? Try to answer this question. See, initialize a queue with V. And we are calling this BFS in a loop. So this can be another good question to ask. How many queues do you use, right?
N queues
in this algorithm.
So you're initializing a queue for every node. So n nodes, n queues.
Really? Think about this. You need to think about this, right?
Okay.
And maybe you need to apply this algorithm on complicated graphs.
Okay.
Right? See, if you get only one queue or n queues, that might not be So simple enough. I want to see a final correct generic, very generic expression, right? So try to answer this question. How many queues will be used in this algorithm? Okay. So similarly, answer that question in this topological sort also. Okay, let's come back to code here, right? So q dot nq, that means whenever the integer is 0, you add it to the queue, mark v as visited, while q is not empty, right? Very similar to it. dq, remove it, dq. T dot add last. Why did we do this? T dot add last. So T is a list, right? List of vertices visited in the topological ordering. So hence you will just add it or append this to the T, right? Finally, we are returning T. This is the topological order. Okay, for each vertex W in V adjacent to U. Now look at this. You dequeued from the queue, and for each vertex adjacent to U, W2, W3, so on WK, let's say, if W is unvisited, if it is unvisited, you decrement the in degree of that. Why do you do this? And if in degree of W is equal to 0, then NQ and mark as visited. See, once you delete this node, right? Deleting this node means you are dequeuing. Deleting this node or adding that node to the T means that you are dequeuing. Once you dequeue, you need to remove all the edges emanating from that vertex. Remember, this is what we said. You need to remove all the edges coming out of that vertex also.
Yes.
What do you mean by removing the edges coming out of that vertex? That means if we remove this edge to W1, we are decrementing the in degree by 1, isn't it?
Yes.
We are decrementing the in degree of W2 by 1. We are decrementing the in degree of W3 by 1, so on. Right? We are decrementing the in degree of each of these vertices by 1 if it is unvisited. If it is visited, we don't care. Right? Okay. So then if in degree of this, any of this is 0, suppose the in degree of this is 0, then you automatically know that for the next step that might be useful. So you add this to the queue. Add this vertex to queue and mark as visited, right? So whenever it is 0, then add this to queue. If it is not 0, you don't need to add yet because it won't be deleted in the next level, right? Only when it is 0, when the in degree of a vertex becomes 0, that will go to the queue. Make sense? Anyway, so it takes some time to understand the entire code, right? So, focus on this, and maybe you can take 1 or 2 examples and, show how the algorithm works on those examples. Let's move to decrease by constant factor. So we will look at 2 problems. Hopefully we will have some time, right? So there are n identical looking balls, but one of the balls is lighter than the other balls. Design an efficient algorithm to detect the lighter ball using a weighing scale or balance. Okay, so you have n identical looking balls. They are identical means you cannot differentiate just by seeing. So one is definitely lighter than the other. You know that one is lighter. Okay, what are you given? You are given a weighing balance. You know, a weighing balance, right? Okay, something like this. So you can have some balls here. In here, you can weigh. So whichever goes up, the other goes down. So that can mean either the lighter ball is here or the heavier ball is here. But there is no heavier ball, right? So this means this has the lighter. Does this make sense? Assuming
Yes.
that you are placing equal number of balls. Okay, so you want to design an efficient algorithm to detect the lighter ball, the index of that, right? Ball. So here is one decrease by constant factor algorithm. So the idea is something like this. Suppose there are 9 balls, right? So we will see the an example first and then generalize the algorithm. Suppose there are 9 balls. 9 divided by 2 is what? 4, right? 4. So place 4 balls on the left pan, 4 balls on the right pan, and there is a remainder, keep it aside. Now you are comparing A and B, right? Left pan, A and B. So there can be 3 outcomes. A is less than B, lighter, right? A is equal to B, or A is greater than B. If A is less than B, that means the lighter ball is here, right? In A. If A is greater than B, then the lighter ball is in B. If A is equal to B, the lighter ball is in C. Make sense? Now, what is the idea? You recursively find the lighter ball in A. You recursively find the lighter ball in B. What about C? The C group will always have at most 1 ball, either 0 or 1 ball, right? So you don't need to recurse. Here you are 100% sure that if this is the case, C has the lighter ball. Make sense? See, having red means the lighter ball is one of those balls. Blue means they are normal balls. There are no problems with these balls, right? Red means the lighter ball appears in one of those red balls. So hence I have shown this as red and this B as red here. Make sense? What is the algorithm? Okay, so here is your algorithm, decrease by half algorithm, right? Like your binary search, very similar to your binary search. Suppose the indices of the balls that we want to determine the lighter ball is from L to H, low to high, L to H. So how many balls are there? H minus L plus 1 balls, right? Numbered something like this. You want to find the index of the lighter ball, right? One of these has the lighter ball. Okay, so the invocation is something like this, 0 to n minus 1, such that n is greater than or equal to 2. Now let's look at this. What is the base case? If L is equal to H, there is only 1 ball in the set, then that itself is the lighter ball. Very simple. The base case is very simple. 1 ball, right? What about if there are more than 1 ball? You want to split in the middle, right? Half is h minus l plus 1 by 2, something like your binary search. You found the mid there, right? You find half. A is the first half of the number of balls from L to H. So it's first half of the balls here from L to L plus half minus 1, first half. B is the second half of the balls, right? Second half number of balls. And what about C? If the number of balls here is odd, then there will be one extra ball, right? Because you are splitting this into two. If the number of balls itself is even, then C will be empty, right? C will be empty. There is no extra ball. Extra ball will always be there if the total number of balls is odd. If it is even, there is no extra ball. Okay. Now we weigh sets A and B, right? We weigh sets A and B. If weight of A is less than weight of B, then you recursively call lighter ball in A. So this was the case 1 as described before, right? Else, if weight of A is greater than weight of B, lighter ball of B. Recursively compute and return lighter ball of B. This was the case 3 in the previous diagram. Else, if weight of A is equal to weight of B, then of course there should be odd number of balls. If it is even, it is impossible to have weight of A is equal to weight of B, because we know for certain that there is a lighter ball. You return lighter ball of C.
Professor, I think there is probably a typo somewhere in the line number 5.
Line number 5, okay.
Yeah, I think the index should go from L plus half up to L plus 2 half minus 1.
Okay, so that's minus 1, or maybe, right, maybe, right? Verify this. Yeah, maybe. Very good. L plus 2 half minus 1. Yeah, maybe, right. So I'll fix this, okay?
Yeah.
Good. So this algorithm is very similar to your binary search, right? So what's the complexity? Number of weighings is, suppose W of n mean the number of weighings for n balls. W of n is equal to W of n by 2 plus 1. So here floor, this is floor, but it doesn't matter. You can just write it as n by 2, right? N by 2 plus 1. Why 1? Because you used one weighing, right, to split into A and B and find which one to recurse. And if there is only one ball, there are no weighings here, 0. Solving, you will get log n base 2. Right? Time complexity is very similar to this, weighings. Okay, so this is log n base 2 weighings. But there is a better algorithm. So what you do is, instead of using divide by half, now you do a ternary search, not binary search, ternary search. Divide n into 3 groups. 3 groups. So here in this example, 9 balls, right? 3, 3, and 3. And apply the same algorithm. If A is less than B, recurse on A. If A is greater than B, recurse on B. If A is equal to B, in the previous algorithm, there was no recursing on B, right? It was just one ball. You can directly print the answer. But here we recurse on C. So there in the previous algorithm, C had only one ball, at most one ball. But here, C can have at most n by 3 balls, right? So we see that the complexity reduces to log n base 3, because in every step, we are splitting n into 3 groups, right? And this will be n by 3. right? Okay, let's see the code. So the pseudocode is something like this. The input is exactly the same, output is exactly the same. Let's look at the logic. There are two base cases here. If L is equal to H, return L, one ball, it is simple. If there are two balls, then return the lighter ball among L and H. So how do you find this? How do you find this? Again, this will require one way, right? That you can do. Okay, so if the number of balls is greater than or equal to 3, what do? Split n into n by 3, right? N by 3 and n minus 2 times n by 3. Yeah, something like this, right? First third, second third, and the remaining balls. And this is the maximum of this is at most 1/3 of the balls. Again, repeat this process. These lines are exactly same as before. There is absolutely no change. So what is the change? Is in the division and one extra base case here. 2 balls instead of just 1 ball, right? 2 balls. You have one extra base case and the division, right? Automatically, the complexity will reduce to log n base 3. Of course, asymptotically, log n base 3 is same as log n base 2. But if you look at the exact number, right, this is much better, right? Log n base 3 is much better than log n base 2. Okay, so this is your decrease by constant factor algorithm. I think we are out of time. We will stop here. We will continue 2 problems in the next session. So we will finish off decrease by conquer in the next session, and we will move to the next topic, right? Probably decrease and conquer. Sorry, divide and conquer. Okay, so we will stop here, team.